Chapter 6, Section 2, Definite Integrals. When we write the integral, this symbol is called the integral, of a function dx from a number a to a number b, we mean all this symbolism means the area between the graph of y equals f of x where f of x appears over here. The area between the graph of y equals f of x and the x-axis from x equals a, which is attached at the bottom of the integral symbol, to x equals b. That's a number attached to the top of the integral symbol. So this is what we mean, but this only applies when the function that is being integrated is greater than or equal to 0 in the interval from a to b. If f of x is less than 0, we'll talk about that later. So this all comes from the Riemann sums in the previous section. So we have any function of x, say it's like this. Suppose x equals a is here on the x-axis, and x equals b is here on the x-axis. This entire function is above the x-axis. That means greater than 0 from a to b. When we slice up this region, which has a curvy top to it, when we slice it up into rectangles, we might use right rectangles, like I'm doing right now. We might use many right rectangles and get something called the right rectangle approximation method. Or we could use left rectangles or midpoint rectangles. Whatever, we add the areas of all the rectangles and we get an approximation for the area between the function and the x-axis from x equals a to x equals b. If we make these rectangles skinnier and skinnier so that we can fit more and more of them in the interval, the approximation gets better. So any one of these rectangles, pick this one right here. Let's say the x coordinate here is x. Right here. Right here. The height of this rectangle, because this point is on the curve y equals f of x, the height of this rectangle that I'm talking about is f of x. It's the y coordinate of this point. The width of the rectangle is delta x. That's how wide each of these rectangles is. And because I'm talking about one specific rectangle, I'm going to say x subscript I, meaning I'm referring to the ith rectangle. Well, all of these rectangles areas can be expressed like this, because every one of them has, for the height, the function value, or the y value, and the width of each of them is delta x, this change in x here. If we add all of those up, from I equals 1, meaning the first rectangle over here on the left, to n, meaning however many rectangles there are, we get the area approximately. see approximately, area between the curve y equals f of x and the x-axis from x equals a to x equals b. I'm just going to say from a to b. That means from x equals a to x equals b. Now, if we could theoretically make infinitely many rectangles here so that each one is very, 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 very skinny, then that means we're going to have the limit of the sum as I goes from the first rectangle to the nth rectangle, where we're going to make n approach infinity of this expression up here. That's the height of each rectangle, and delta x is the width of each rectangle. If we could do this, make infinitely many rectangles in there, then we would have what's called the integral of the function. And the dx is just taking the place of the delta x. The f of x is taking the place of x sub I. And the a and the b are just telling us that I attach here. That's just saying where the interval starts and where it ends. So we're now going to do some exercises on page 286. Page 286, exercise 10, says integral -4 to -1 pi over 2 d theta. These exercises are meant to learn what the symbol means. This symbolism, gibberish, means make a y-axis as usual, and what we ordinarily call the x-axis, because I see d theta here, we call it the theta axis. And we're going to graph y equals whatever's right here. I'm going to call that the integrand. So let y equal the integrand. And y equals pi over 2, the graph of y equals pi over 2 is a horizontal line. It looks like this. So we're graphing y equals this integrand. And we're going to look at the region between this function, which is a horizontal line, and the theta axis, or x-axis, from x equals -4, let's say that's here, to x equals -1. That's here. In other words, this question right here is simply saying to you, what is the area of this green rectangle? Because the region between y equals the integrand and the x-axis, from this number, -4, to this number, -1, that area is a rectangle. So the value of this is this side of the triangle, which is -1 minus -4, which is 3, times the height of this rectangle, which is pi over 2. So the answer to exercise 10 is 3 times pi over 2. That's that. All right, next one we're going to do is number 14. It's 287, 14. It looks like this, the integral from 1/2 to 3/2 of -2x plus 4 dx. The dx, or in the last one d theta, is just a symbol that we do nothing with, really nothing, except it tells me to make this the x-axis. If it said dz, I would have made this the z-axis. And we are going to graph y equals the integrand, y equals -2x plus 4, which I hope we know is a line. To graph a line, I can make a table. I know I'm going to start at 1/2 because that's at the bottom of the integral symbol. And I have to go up to 3/2. So what is y when x is 1/2? In other words, what's -2 times 1/2 plus 4? I think that's 3. when x is 3 halves, y is negative 2 times 3 halves plus 4, which is the same as negative 3 plus 4, which is 1. The point 1/2, 3 is, let's say that's here, and the point 3 halves, 1, so that's here. So we know this is a line, so a line with slope negative 2. When we see this, it's pretty fancy. It means the area between y equals negative 2x plus 4, this anchored thing, and the x-axis, the x, you know, he tells me that's a border, from x equals 1/2, which is here, to x equals 3 halves. So this is just saying find the area of this green region, which is called a trapezoid. Please learn that the area of a trapezoid is 1/2 the height times base 1 plus base 2. It's important to learn this. It's a big, important thing in calculus. The area of a trapezoid. The B1 and B2 are the bases. Base does not mean bottom. The bases of a trapezoid are the parallel sides. Those are the bases of the trapezoid. The H, you say height, but that means the distance between the parallel sides, the distance between the bases. So these blue sides are parallel, they're B1 and B2. This longer base is 3, this shorter base is 1. So here's B1 plus B2, base 1 plus base 2. The height, that's the distance between the bases. That's the distance between 1/2 and 3 halves, which is 1. And the 1/2 is part of the formula. The area of a trapezoid is 1/2 the height times base 1 plus base 2. So the answer to exercise 14 is 2. Next one is number 16. Integral from -4 to 0 of the square root of 16 minus x squared dx. dx doesn't serve much of a purpose. It's always going to be there though. I know I need the x-axis, and the other axis can be called y as usual. We need to see y equals the integrand. That means y equals the square root of 16 minus x squared. If you square both sides of this equation, you'll get y squared equals 16 minus x squared. If you add x squared to both sides, you get x squared plus y squared equals 16. So we know this is the equation of a circle with center 0, 0, and radius 4. So center 0, 0, radius 4, radius 4, radius 4. But the original up here does not say y equals plus or minus the square root. As x squared plus y squared equals 16 is a circle. Up here, y equals this integrand is just a semicircle. It's just the positive side of the circle. That means the top of the circle. And it's a circle with center 0, 0, radius 4, if we were to make the whole circle. The integral of radical 16 minus x squared dx from -4 to 0 means the area between y equals the integrand and the x-axis from this x value, -4, to this x value. That means that this is asking for the area of this quarter of a circle. The area of the circle is pi r squared. that's not a circle, it's a quarter of a circle. So we do this, and the radius of the whole circle is 4. So we're going to say pi times 4 squared over 4. So 4 pi is the answer to this question. This is equal to 4 pi. Next one is number 18. The integral from -1 to 1 of 1 minus the absolute value of x dx. We know y equals the absolute value of x is the v-shaped point at 0, 0. A negative in front means flip this over the x-axis. This is y equals the absolute value of x. This is y equals the absolute value of x with a negative in front of it. And then adding 1 to that means shift this graph 1 unit up. Take this graph and add 1. So instead of the point at 0, 0, it's going to be at 0, 1. X-axis, y-axis. It just so happens that this crosses the x-axis at -1 and 1, because in this equation y equals the integrand when x is -1, or when x is 1, y is 0. That's why we need the point 1, 0 and -1, 0. We need those points. And 0, 1, because when x is 0, y is 1. So this means we are looking for the area between y equals the integrand, which is blue, and the x-axis. That's the x-axis. From x equals -1 to x equals 1. So the numbers are attached to it. So we need the area of this triangle. And everybody knows the area of a triangle is 1/2 the base times the height. The base of this triangle is 2. From -1 to 1, that distance is 2. The height of the rectangle is 1. So the answer to exercise 18 is 1. The next one is going to be number 40. Page 287. The integral from -5 to 6 of 9 minus x squared over x minus 3 dx. We, as usual, we're going to graph the integrand. We're going to graph y equals the integrand, which will be a little bit easier to graph, a lot easier to graph if we simplify this. That's 3 plus x times 3 minus x over x minus 3. That can be simplified to y equals -1 times x plus 3, because 3 minus x and x minus 3 are opposites. Anything divided by its opposite is -1. We have y equals -x, -3, which is a line. The graph of this is a line. The graph of this would be a line with a hole at x equals 3. Since the original integrand does not exist when x is 3. So we're still going to graph this line and then just make a hole in it at x equals 3. When x is -5, the starting number, what is y? -5, that's 5 minus 3. When x is, usually we go to 6 next, but I'm going to go to 3 to see where the hole is. When x is 3, -3 minus 3 is -6. And when x is 6, that's the ending point of this interval, -6, -3 is -9. So this graph, the graph of this integrand, y equals 2, contains the points -5, -2, -5, 2, and 3, -6, but actually that would be a hole in the graph. -6 and 6, -9, if I can fit it, over 6 and down 9. So if y equals 9 minus x squared over x minus 3 is this line. It's this little hole in it. You got some extras. So this question up here, this question means find the area between y equals the integrand and the x-axis from the x equals -5 all the way up to x equals 6. And this is crossing the x-axis. It crosses the x-axis when y is 0, which would be when x is -3. So it's -3 is 3 minus 3. So this might be not done to scale, but the numbers are correct. Since part of this graph is below the x-axis, the integral is going to be this green area, or this red area. That'll be a positive number because that is above the x-axis. And the integral from -3 to 6, since all of this blue is below the x-axis, the integral is a negative number. Since the blue region is below the x-axis, the integral is a negative number. So we're splitting this problem into two parts, -5 to 6. So we're going to go from -5 to 3, get an answer, from -3 to 6, and get another answer, and then just put the two answers together. So the red is a triangle. The area of the triangle is 1/2 the base times the height. The base of this rectangle is 2. That's how far it is from -3 to -5. And the height of that triangle is also 2. So look over here, and that's -5 is 2. So the integral from -5 to -3 is in red here. The blue part from -3 to 6, also a triangle. The area of the triangle is 1/2 base times height. The base of this triangle goes from -3 all the way to 6. So the base of the triangle is 9. The height of the triangle is also 9. The side of the triangle right here is 9 because it's over here. But this blue value is a negative number. The area is a positive number. And I said, what is the area of this region? You would say a positive number. Area is positive. But integrals can be negative. And that's just when the region is below the x-axis. So in front of the red, there's a positive because the red region is above the x-axis. In front of the blue, there's a negative number there, or negative sign there, because the blue region is below the x-axis. 1/2 times 2 times 2 is 2. And 1/2 times 9 times 9 is 81 halves. Don't forget the negative in front of that. 2 is the same as 4 halves. 4 halves minus 81 halves is -77 halves. This is the answer to exercise 40.